Welcome to Lecture 16, NPTEL Online Certification course on Bioreactors. In the previous lecture, we had assigned a problem. In this lecture, let us go ahead and solve that problem. This is the practice problem 4.1. The problem reads, the following data was obtained during KLA determination of a stirred tank bioreactor operating at 500 rpm, 1 atmosphere and 37 degrees C by the dynamic response method. The oxygen source was air. A millivolt meter was used to read the dissolved oxygen level. Find the KLA of the bioreactor. What is given here is time and dissolved oxygen in millivolts. Okay. Let's go ahead and solve the problem. I'll explain this a little better during the solution itself. We will ask our usual questions for closed-ended problems. What is needed? The KLA of the bioreactor by the dynamic response method. What is known or given? The data on millivolt versus time during the oxygen sorption process in the bioreactor in the absence of cells. Okay, the dynamic response method. If you recall the dissolved oxygen probe, its working principle, it's an electrochemical principle. There is cathode, the platinum, there is an anode. There is a slight mix up in the lecture. Platinum is the cathode, silver is the anode. And then these have to be in an electrolyte for an electrochemical system. The electrolyte happens to be KCl. These are placed in a housing which is dipped into the broth in which the dissolved oxygen level needs to be measured, and this housing is covered with an oxygen permeable membrane. The rate at which oxygen permeates through the membrane and reaches the electrochemical cell is proportional to the current that is generated by these two electrodes in the electrolyte, and therefore the oxygen level can be directly related to the current. In this example, the current is directly given instead of percentage air saturation. The current is what is actually measured, and then there is a conversion that takes place electronically in the meters available nowadays to give you air saturation by calibration. Here we will deal with millivolts themselves as direct indicators of the dissolved oxygen level, which is the bare minimum. As I mentioned, this happens to be my own data from my doctoral studies, and I had used a millivolt meter to measure DO under these circumstances. This is one of my own the KLA measurement data. So we are going to use millivolts as measure of dissolved oxygen. We also know that the conditions are bioreactor conditions are the stirrer is rotating at 500 rpm. The pressure is 1 atmosphere, temperature is 37 degrees C. As mentioned in the lecture, all these parameters, the agitation level, RPM, aeration level, liters per minute or volume per minute, and so on, temperature, pressure, all these have significant impact on the KLA value. The changes in these will change the KLA value. So what is normally done while finding the KLA is to set all these conditions at the operating conditions and measure the KLA. That gives us an idea of the oxygen transfer capacity or oxygen supply capacity of the bioreactor. The third question, how to connect what is needed to what is given. We have already derived that log of C star by C star minus CO2. CO2 is the dissolved oxygen level concentration. The C star is the concentration in the liquid phase that is in equilibrium with the gas phase oxygen concentration. That equals KLA times T. Y equals mx. This is y and T is x. KLA is the slope. Therefore, if you plot log of C star by C star minus CO2 versus T, we'll get KLA as a slope. right? And now I think we'll go to the spreadsheet in which the calculations were done. Yes. You see here, this is the same data, the time versus dissolved oxygen in millivolts. I'm calculating natural log C star by C star minus C. To find C star, let us look at this data. The DO level increases and reaches a constant value here, 1.1, 1.1. So this indicates that the liquid has reached saturation or equilibrium condition with the gas phase, which is air here. So this millivolt value is directly proportional to C star, and therefore let us take it as C star. If you take the constant as k C star by k into C star minus C, k will cancel out, so the dissolved oxygen concentration is directly proportional to the millivolt value here. The constant of proportionality does not matter. So 1.1 is taken as this. If you look at the formula here, natural log of 1.1 divided by, in the denominator, 1.1 minus the DO value in terms of millivolts. That's the way this is calculated, and these are assigned to the same times that are given here. If we plot log of C star by C star minus C versus time, you get a curve something like this. However, we can use that particular equation only in the linear regime for oxygen sorption. This is a non-linear regime here, that is to be expected. The linearity probably starts here and goes up. Therefore, we are going to look only at this region for calculation of KLA. We are going to look at only the slope of this particular region. We are going to drop the first 3 points which are in the nonlinear region. If we do that, then we get a curve like this. This is plot of log of C star by C star minus C versus time. As you can see, about 56 is the point, 56 seconds is the point at which the linearity began. We used all the points here. Of course, this is experimental data, so you don't expect it to always fall on an exact strict line. This is good enough. The R squared value is about 0.94. That's probably the best that is obtainable from this particular data. And this is the equation, the fitted equation. The slope is 0.0914. Therefore, 0.0914, this is in seconds, so the slope will be in second inverse, 0.0914 second inverse. We typically provide KLA in per hour. That's easy to make sense because we normally look at KLA values on a per hour basis. On a per hour basis, this turns out to be on a per second basis into 3600 or 329 hour inverse. That's quite a large KLA for this reactor, but that's what it is. Okay, so that is the solution to the problem. When we meet next, we will go forward with the information in module 4. See you then.